Okay, so what we have here is an experiment which Mr. Baker normally does as a class experiment with you, and I've just tried to come up with a version of it that's perhaps a little more accurate, but I'm not going to guarantee that because I'm going to do it a little bit rough and ready. But what we're going to try and do is investigate the difference between a driven system that's undamped and a driven system which is strongly damped. So this is set up in the undamped mode at the moment, and no doubt you can see what I've got here. I've got a vibration generator running off a SIGGEN. I'm using the older SIGGENs because they've got tenths of a steps marked out in tenths, which you might remember is a problem with the newer SIGGENs. So vibration generator is going up and down into a spring, and then attached to the other end of the spring is a weight, and I've just got them running over one of our data logger pulleys so I can measure how much it's moving by how much the data logger pulley is moving backwards and forwards. You'll do a very similar experiment as one of your required practicals when we're back in school, where instead of it being driven, as is the case here, you just use the data logger set up this way to find out what the natural frequency of the spring mass system is. Now, you actually need to know what the natural frequency of the spring mass system is in order to interpret this experiment, but you know that because bouncing away there is one of our normal disposable springs, and one of the experiments that we did earlier on in the year was to work out what their K constant was. So you know what that is, it's in your lab book, and that's a 200 gram mass, or 0.2 of a kilogram, bouncing up and down on the end there. So you can work out what the natural frequency of this system should be. The usual way to plot the graph I'm going to ask you to plot is for your x-axis to be the ratio between the natural frequency of the system and the driver frequency. So you divide the driver frequency by the natural frequency of the system so that resonance should occur at 1 on the x-axis. It doesn't massively matter if you don't do that, but if you want to do it properly, that's what you should do. Right, you can see I've got our laptop there, so I'm going to do all the operation from the other side. So I'm going to pause this now and set everything up so that we're ready to go. Okay, so I've switched this around to the other side so that you can see the laptop screen and what I'm doing with the signal generator. At the moment, it's running at 1.6 hertz. Because I'm on the times 1 hertz frequency range, and it's reading 1.6 off my dial. I'm going to start off at a different one, but when I start much lower, it's not going to show up. So I'm actually going to start down on the 0.1 scale. You'll see now that the vibration generator only going up and down every few seconds. There you go. I've put it up to 0.5, so that means that my time period is 2 seconds. And what you can no doubt see is that all that's really happening with the spring is that it's going up and down with the SIGGEN. So at a long way from resonance, which is where we are now, the vibration generator and the driven system are all completely in phase because it's just really just going up and down with the SIGGEN. But we want a value for that, so I'm just going to try and get a value for what's going on. Messy. Hard to know there what's really a measurement and what's not. But you can see here that I'm going to do this twice. I'm going to do it undamped and I'm going to do damped. I'm going to vary the frequency and I'm going to measure the maximum and the minimum displacement on this maximum and minimum displacement on the system. Now I haven't put any units in for maximum and minimum displacement because although it does say millimeters on your computer screen, it's not really measuring in millimeters. The units are what we might call arbitrary units. So I haven't even bothered writing arbitrary units in. I guess you should do really. Okay, let's see if I can get a value from this. So maximum value there is 24.7. The only question in my head is where is the zero? Where's the lowest value? Somewhere around there? Hard to know really. Let's call that a minimum 15.7. Right, I'm going to go up to 6. And perhaps more clearly see the double bounce here at 0.6 hertz. We're not really interested in that double bounce. We're only interested in the displacement. So put it on values again. Maximum 23.8 and minimum somewhere around there. What, 11.2 was the lowest that showed? Okay, I'm going to go up to 0.7. Starting to get quite messy now, and that of course is because we're starting to get a shift in phase, and so what the spring's wanting to do and what the driver's doing are no longer quite the same, and so we're getting this odd double bounce thing going on. Let's have a look what we've got here. 24.7 again and 9.9. Up to 0.7, pop it up to 0.8. Now, if you had to guess, you'd say 0.8 was something like half of the natural frequency, because the spring is bouncing up and down twice for every one oscillation. So it looks like we're pretty close to a resonance at halfway. Right, I'm just going slightly out of bounds there, aren't I? So I'm just going to increase my scale a bit. Okay, so which one's the true bounce? That one, maximum 55.6 and a minimum of minus 19.5. Okay, that was at 0.8. Let's go up to 0.9. Yeah, that's more sensible. I've moved away from that resonance. Yeah, press the wrong button. Apologies. Much more like the kind of thing we were expecting. So what have we got? 14 up to 32. So 32 is my maximum, 14 is my minimum. Put it up to 1 hertz. One hertz. 16.8 up to 29.8. Okay, going to have to switch ranges now. I'm just going to turn it down whilst I do that so I don't upset it too badly. Right, this is 1 Hertz again on the new range. I just want to double check that they give roughly the same answer on the 2 different ranges. Make sure that the signal is really doing what it's supposed to be doing. Hopefully you've got something that looks a bit like that. $33.3 down to 13.3, so slightly bigger oscillations there, so not quite the same value as it was when it was apparently on 1 on the other one. Okay, we're going to go up to 1.2. Hopefully you can see on the screen there that the pull and the bounce are now completely out of phase. We're sort of losing that double bounce, but we're getting the phase difference between what's going on the driven mass and what's going on with the driver. That's important for you to understand for resonance. So consequently, it looks like it's settled down a little bit. Bottom of 17.1 to a top of, what's that, 29.7. Okay, 1.4. So you can really see now when the SIG-Jan goes down and the spring goes up. They're out of time. 1.4, giving me values of 32.8 as a maximum and 15.3 as a bottom. I'm going to try and go halfway, so I'm going to call this 1.5 because we're getting clear near to resonance now. Yeah, see that straight away, that's bigger. So 6.8 down to 12. One point six. 44.8 down to 5. Now, question is 1.7 out of resonance or is 1.7 past it? Looks like it's about there, doesn't it? And suddenly got very excitable. Trouble is, when it does this, there's a risk of it shaking itself to pieces. And look at the spring, the string's actually going slack. Right, put that at 1.8 and hopefully that will be past the resonance and it'll calm down a bit. Yeah, and there you go. Right, so we're still reading 1.7, doing the 1.7 reading, sorry. And the values for 1.7 are top is 81.6 and bottom is minus 25.0. Right, running on 1.8. Top is 65.4, bottom is 20.6. .2. Right, 1.9. Keep pressing the wrong buttons. See, it's dropped right back off again now. .8 for the maximum. This is 1.9 hertz down to 29.1. 2 hertz. .3 down to 34.6. Right. 2.2. See how different the phase is now. .5 down to 40.3. Right, 2.4. .1, 42.2. .6. I'm running out of space, so I'm thinking I'm not going to do many more. .2, 43.8. Right, let's pop it all the way up to 3. There you go, look, hopefully you can see that line on the graph. The thing is barely moving now by comparison with what it was doing at resonance. And so I'm getting a peak at 48.3 and I'm getting a bottom at 44.9. 48.3, 44.9. Okay, so I'm going to pause things there and change and put my damping on, which is going to be my weight bouncing up and down in a bucket of water. Okay, can you see my weight sitting in the water? Now, let's see how much this moves now. Before I do that, I'm going to just try and re-zero it. And I'm going to bring my scale back down because we're not expecting it to bounce anything like as much this time, are we? Minus 50. Plus 50. Okay, so same thing. I'm going to start right down at 0.5. All the rest of the settings are the same. There we go, very much the same shape as we were getting before. With a maximum of 15.5 and a minimum of 3.1. 0.6. Looks very similar. Maximum 15.1 and a minimum of 1.8, 0.7. A bit bigger now. We've got that same resonance, double bounce resonance thing going on that we had going on before. So I've got a maximum of 18.4 and a minimum of minus 3.1. Point 8. So maximum of 14.4 and a minimum of minus 2.4. 0.9. Calm back down a little bit because we've come away from that resonance. So maximum of 12.5 and a minimum of minus 1.3. And 1. So maximum of 13.1 and a minimum of 1.3, minus 1.3. Right, I'm going to switch it back up to the higher range again now. Oops, oh, not good. Fine. And so we're going to repeat 1 on the higher range. Just to check it's doing pretty much the same thing. And what have we got? 12.5 down to minus 1.1. Not quite the same. Close. Okay, 1.2 was next, wasn't it? Right, doing a bit more now. Only a little bit. So 1.2. We've got a maximum there of what, 13.8? And a minimum of minus 1.7. Next one was 1.4. So 1.4. I've got a maximum there of 19.5 and a minimum of minus 5.5. Right, when we did this before, we went up in 0.1 steps from now. As close to 0.1 steps as I can actually manage on this dial, but we'll give it a go. Right, this one should be 1.5. .5, 24.7 down to 24.7 down to minus 8.5, 1.6. Right, if you remember before, at this point it was going nuts. Right now, actually, that hasn't changed a whole lot. So this is 1.6 and the values are 24.3 down to minus 6.3, 24.3 down to minus 6.3. So not much of a change. Now let's put it up to the big one, see whether it works. Okay, so I'm on 1.7. And that very clearly has not increased. So I've got a maximum of 20.4 and I've got a minimum of minus 2.2. So there you go, it's actually started to go down. And that, of course, is one of the things that you'll have to know about damping and resonance, is that the adding damping to resonance not only broadens the peak, but moves the peak to very slightly lower frequencies. 1.8. Just jigging about a bit. I might just leave it. Not very happy with that one. So let's just take them from up this end. 1.8. What's that? Maximum of 18? 18.4. And a minimum of 2. 1.9. 17.3 down to, what's that, 3.7. So 17.3 down to 3.7. Two. $16.2 down to 4.2. What was next? 2.2. $13.8 down to 6.8. $2.4. So 13.1 down to 7.7. $2.6. I've got smooth curves over here somewhere. So 12.3 down to 8.7. And the last one I did before was 3, jumped up to the higher frequency. Let's jump up to 3 then. That's a nice bit of the curve. So I'm going to go like 11.8 down to 9. Okay, that's it. You need to plot up the displacement. I would just do the difference between the max and the min, but if you properly wanted to do amplitude, it would be the difference between the max and the min halved against frequency on your x-axis. But as I said to you, traditionally, you don't actually put frequency on your x-axis. You put frequency divided by the natural frequency of the oscillatory system. So you need to look at what your value for K was to work out what the natural frequency of the oscillatory system is, and then divide those frequencies through by that to go on your x-axis. You'll do a proper job. Hopefully, you've got data looks a bit like that.